Okay, so today is going to be the first day we are going to start working on the propulsion part of the course. I guess everyone's happy, which is good. And this essentially means that we are not going to use the thermodynamics book anymore, and we are going to use the propulsion book. The title, I don't remember the exact title of the book, but it should be Introduction to Rocket Propulsion, something like that, right? And we are going to cover the chapter 1. Chapter 1 is just an introduction to the whole book, to the course, to the book itself, and also an introduction to propulsion, jet propulsion specifically, right? And your homework 2, which is based on this one chapter, is posted online. Your homework 2 is essentially the 5 exercises at the end of chapter 1, right? So I have a printout of chapter 1 here. These are just 5 very simple exercises. You essentially have to work with we are only going to see 2 equations. This is 5 exercises based on those 2 equations, but they're a little creative. So you have to think about them a little bit. You have to make sure you understand how to optimize an equation, how to get the minimum and maximum. The questions themselves are not that hard to figure out, but you have to be just a little creative, right? It is not just plug and chug. Okay. Any questions? No? And your homework 2 is going to be due next Wednesday, right? That is when I'm going to post your homework 3, which is going to be due the Wednesday after that, so in 2 weeks. And that is the day we are going to have the first exam. Okay? So keep that in mind. You can actually double check that just to make sure I'm not giving you any wrong dates. Exam 1. So we are at September 22nd today, right? We are here, right now. And we are going to start the chapter 1. We are 1 lecture behind because I had to cancel the other lecture last week. We are 1 lecture behind. We are going to talk about chapter 1 of this book today, and then we are going to move on to compressor flow. Probably what I'm going to do is I'm going to let go of this exam review part, and we're going to continue the discussion on the compressor flow. But this essentially means that we are not going to have a review for exam 1. Maybe half of the class, but not a. What do you guys think about this? Do you think a review is something that you guys that is necessary, or?
Is exam 1 going to be on just the propulsion part of it, or is it going to include thermodynamics?
Thermo and propulsion. Thermo, for whatever reason, you guys think thermo is separate from propulsion. If you don't understand thermo, you don't understand propulsion. Okay? So you have to understand the thermo part of it. And that the reason I actually included thermo part of it, I didn't do this last year, the reason I included the thermo part of it was because the students didn't know the thermo part of it, so we had to go a little deeper. Okay, we had to go back actually, do a reminder. Any questions? So you guys don't think it's necessary to do a review? Okay, so, and I guess everyone is on board with this. So what we are going to do is that we are going to, if we couldn't finish chapter 2 of the book, which is very possible, chapter 2 is a very large chapter. If you couldn't finish chapter 2 of the book, we are going to, I'm going to give you the exam just up to the parts that we have covered, right? Yeah, so, but just keep in mind that your exam is going to be on October 6th, which is the fall break. Just the day before the fall break. So you take the exam, and then you go off to fall break, either to party or drink a lot of alcohol. Depends on how you perform your exam, right? Hopefully this first one.
How are we going to do the tests? Are we going to be in class or?
In class, yeah. Tests are going to be in class, yeah. I don't like online tests because of a host of reasons. First one is when you are doing online tests, asking a question during an exam is very difficult, right? And I guess all of you have had online exams, and I guess you can all agree to this. And also, if you're a cheater, which I am assuming, hopefully none of you are, it is going to be easier for you guys to cheat. If you are here in class and if you cheat, that's right. If you're like brave enough to cheat in front of me, good for you. Go, do it. Yeah, I mean you don't have to be a pretty good cheater, but you should be an okay cheater, but you have to be very brave, right? Especially in front of a bald guy with a beard. I mean, it's just intimidating, right? But in an online section, you can actually look online. I don't really like the setting like that, because it is going to be unfair to everyone. Okay. So if there's no other questions, let's go ahead and start this chapter 1. This chapter 1 is essentially a review. It's very light on mathematics, and I'm happy we are doing this because I got the feeling that you guys are a little exhausted by the amount of mathematics we were working with in the previous lecture. So we are going to be a little light on mathematics. The first part of the chapter 1 is a historical perspective on propulsion. So essentially, powered flight started with the Wright brothers, right? In 1903, they started their whole thing, but I think they flew the first plane in 1907 or 1911, something like that, right? But who knows the exact year? I can't say off the top. What's that? 1911 then. Okay. Yeah, so that's where they had their first successful flight, but they started the whole project. They started building the aircraft in 1903. So first powered flight was 1903. What kind of engine did they use for that flight?
Reciprocating combustion engine.
I guess I say that here. Yeah, it was a 12 horsepower, very small engine. It was an internal combustion engine, right? Which essentially, what is an internal combustion engine? You have a piston that is moving up and down in a cylinder. Not the most efficient way of flying. That's why the flight took like a couple of minutes or like 2 or 3 minutes. So in order to combat this efficiency problem, this guy, Frank Whittle, a British guy actually, came up with the idea of the jet engines, right? He actually patented the jet engines and gas turbines in general. Patented the jet engine, but the Germans beat them in manufacturing the engine. So Germans, there's this other guy, I forgot his name. What's that? That's the first aircraft, right, with the jet engine. But the guy's name is like, it starts with an O and it has an H in it. But we're going to see it later. So the first guy who patented the idea of the jet engine was this Whittle, right? And in his engine, and I'm pretty sure you are well aware by this point that in his engine he used a Brayton cycle instead of an Otto cycle or a diesel cycle, right? What were the specifics of a Brayton cycle? Who can tell me off the top of their head? What did we have in a Brayton cycle? What did the cycle include? A compression. We had compression in a compressor, right? Then we had the combustor stage in which we added fuel to the air, and we have an air-fuel mixture, and we have the combustion, and then the turbine, and then we have the exhaust nozzle, right? It's usually an open Brayton cycle. His patent, this is taken from his patent. This is his idea on the patent. You can see the diagrams, the TS diagrams here, all of the thermodynamic diagrams, and also the engine itself is the schematics of the engine itself here. All of these parameters, the specific consumption, thrust, and the exhaust temperatures, which are the important design parameters in an engine design, were also given in the patent. One thing that was different in his patent compared to other engines. I mean, there were a couple of things that were different. The first thing was the compressor. Based on the schematics you see here, what do you think the difference was between his engine and a regular, the compressor part of the engine? This is the compressor part, right, as you can see. What is weird about this compressor? Okay, so as Kerem said, the air is coming in like this and goes to the combustor like this, the turbine and combustor, all of the system. This is because he is using a centrifugal compressor, right? But the centrifugal compressors are rarely used anymore. I mean, they're used, but not as much as an axial compressor. In an axial compressor, air comes in, you have the blades, you have the whole compressor system, and then the compressed air goes out at the end, right? But here, you have the centrifugal with the centrifugal blades and everything, so the direction of the flow changes after the compressor, right? That's the idea of the centrifugal compressor. And then we also have the reverse flow combustors. So the compressed air comes here, and then the combustors pushes air back into the turbine blades. Not a very, I would say, to my mind, to me, it is not a very efficient way of doing this. But the problem at the time was the design of this. I mean, they didn't have this efficient combustors we have nowadays, right? All of the systems we have because we have made some advances in some other fields, right? So at the time, it was the best thing this guy could come up with. And this engine is called the W1. This is a W2 engine. This one is a W1 engine, but essentially the same ideas and the same, and it's just a little bit of improvement to the W1 engine. So let's take a look at his, this is a movie from Smithsonian on
His name is Frank Whittle, and he'll make the greatest contribution to aviation since the Wright brothers.
The thought, get rid of the piston engine and substitute a turbine, you might say that came out of the blue.
Professional jealousy robs Whittle of the funding he needs to build a prototype.
A piston engine goes 2,000 RPM. These engines are going to be turning 16,000.
So the reason he couldn't manufacture the engine and the reason Germans beat them to the manufacturing was based on what Smithsonian is saying is professional jealousy of someone.
His name is Frank Whittle, and he'll make the greatest contribution to aviation since the Wright brothers.
The thought, get rid of the piston engine and substitute a turbine, you might say that came out of the blue.
Professional jealousy robs Whittle of the funding he needs to build a prototype.
A piston engine goes 2,000 RPM. These engines are going to be turning 16,000 RPM. And so this is a lot of high-speed motion that has to be quelled with mechanical engineering solutions.
Whittle's big challenge is a material science challenge, and that is you have to find a way to enclose this combustion to the point that it escapes then through the nozzle of the engine without destroying the engine.
He needs high strength, alloys that actually can withstand the high temperature in excess of 1,000 degrees, which can put a lot of stress and strain on the physical structure.
These mechanical challenges and little money mean that Whittle suffers many setbacks, one of which in April 1937 he'll never forget.
Father was in charge of the fuel control, and he was signaling somebody else to get the starter motor up to speed. Then he starts putting fuel in. The engine began to accelerate. Fine, that's what they were hoping it would do. But the trouble was that it just carried on accelerating, which he couldn't understand. It was frightening because it went from a sort of a growl to a scream, got up to about 8,000 RPM. Fuel had collected in the bottom of this rather ramshackle combustion chamber, and that's what was keeping the engine going, what it was accelerating itself on.
Excess fuel is pooling in the combustion chambers. Whittle has lost control over the engine's speed.
One of the great difficulties was finding a way to govern the engine, to find just the right amount of fuel to get a steady, productive combustion, but not so much fuel that it would cause the engine to accelerate completely out of control and come completely apart.
And he stood there, and he wondered what on earth had happened. And he looked around, and there was nobody around. All the mechanics had done a bunk.
Through the 1930s, Whittle refines his invention into a marvel of design and material science that will eventually change the world.
Okay. We should talk about this part later. I don't know why is this here. But so as I said, Germans actually, his name is Ohain. I don't know the pronunciation. That's how I pronounce it. Von Ohain, whatever. This German invented a turbojet engine in Germany that was going to patent later in 1936. But he could manufacture this earlier than this guy. The difference between German's engineering, the German engine, and the British engine was that the British engine actually could produce only 250 pounds of thrust, whereas the German engine could produce 2,000 pounds of thrust. So 8 times more powerful, right? Which essentially means that the Germans could use it readily, which they did, unfortunately, in the World War, right? And this is the actual plane that Kerr mentioned. Again, might have trouble pronouncing the name, Messerschmitt 262, which was the second turbojet plane, but it was the first one ever that was mass-produced, right? The second plane that was ever used the turbojet engine, but it was the first one that was mass-produced and was used actually in the war. This engine has 2 of these jet engine designs. 2, it's called the Jumo 004B turbojet engines. Let's actually watch 2 more clips about the first ever turbojet.
In 1936, von Ohain approached German aircraft designer Ernst Heinkel for support.
Heinkel's engineers were understandably pretty skeptical about it, but Heinkel had a personal fetish for high altitude, high performance, and he decided if there's anything in this revolutionary new concept, he wanted part of the action.
On August 27, 1939, the Heinkel HE-178 became the world's first jet-propelled aircraft. Producing 1,100 pounds of thrust, the engine pushed the plane to speeds of 435 miles per hour. But it burned fuel at such a high rate, it could only remain airborne for 10 minutes. However, just 5 days later, Hitler invaded Poland, and the pioneering feat was all but forgotten.
I guess that the thing that happened after 5 days was a little more important than the jet engine at the time. So they stopped the development. But the problem with this first ever jet engine was that it couldn't fly more than 10 minutes, right? I mean, it didn't produce that much thrust compared to the second version of it, right? But it also couldn't produce, couldn't stay airborne for more than 10 minutes. This one is about I think this is the last, not the last clip, but this is the last long clip. Maybe we're gonna see. How do you guys enjoy these videos? You like them? Okay. I mean, I can't really have that many videos in my lectures, so that's mathematics, right?
Messerschmitt Me-262, German jet fighter, World War II. Nazi Germany was a strong supporter of jet technology.
I'm sorry. I don't know what.
Messerschmitt Me-262, German jet fighter, World War II. Nazi Germany was a strong supporter of jet technology and developed the first turbojet-powered aircraft called the Heinkel HE-178, which flew in 1939, only days before the German invasion of Poland. The Messerschmitt Me-262 was not the first fighter jet in World War II. This was the Heinkel HE-280, although it would emerge several months before the British Gloucester Meteor. Nevertheless, the ME-262 was an advanced design in the war that signaled the dawning of the jet age. It was sleek in appearance with swept wings and a powerful armament. Under secret development for several years as Project 1065, before the war had even started, the ME-262 prototype was ready in 1940, with a Junkers Jumo 210 piston engine turning the propeller because of delays in the intended turbojets. The first test flight of the ME-262 V1 was on April 18, 1941. On July 18, 1942, the ME-262, now in its third prototype phase, flew for the first time with turbojets. Its power plant were two Junkers Jumo 004 turbojets. While these were better than the previously tested BMW 003 engines, they had a short operational lifespan of just 20 to 25 hours due to shortages of heat-resistant materials. The jet had a maximum speed of 900 kilometers per hour, or 559 miles per hour, and would be difficult to maneuver for the inexperienced pilots training with this new machine. The ME-262 impressed many, including the famous German air ace Adolf Galland.
Sorry, it's just a little too... No.
Measured. Some of the major variants were the Hunter, nicknamed the Swallow, the Bomber, nicknamed the Stormbird, and an experimental two-seater Night Fighter. In its bomber role, it was armed with two 250-kilogram bombs, but with no bomb sights, targeting accuracy was difficult. As a fighter, and therefore without the weight of bombs, it was deadly against Allied aircraft. It was armed with four 30mm Mk-108 cannons. The jet could also be fitted with 24 R-4M rockets, which could take down a B-17 bomber with ease. In less than a year of operational service, the ME-262 had proven that it was an effective, innovative weapon against the Allied bombers and their escorts. The jet fighter first saw action in the summer of 1944. In August, the first ME-262, lost to the enemy, was shot down by a P-47 Thunderbolt. The unit JV-44, commanded by General Adolf Galland, saw much success against enemy bombers with a 4-to-1 kill ratio. While it was much faster than the P-51 Mustang, it was less maneuverable, which U.S. pilots took advantage of when the ME-262 was making turns. It would also be vulnerable to enemy aircraft during takeoff and landing on runways. For Germany, the ME-262 came into the war too late. Allied bombing made production difficult, and only 1,433 total ME-262s would be built. After the war, Czechoslovakia also produced and flew their own ME-262s. If the history of the ME-262 excited you, try unlocking it in War Thunder and dominate the skies against all the...
Yeah, you can go and play that game as well. That wasn't sponsored by me. Okay, so let's take a look at the engine. The engine of this, the Jumo, right? The Jumo 004B engine. Essentially here, as you can see, we have the actual compressor. Instead of centrifugal compressor, we have the actual compressor, which is an achievement. Then we have the combustors and the turbines and also the exhaust nozzle. We have actually some sort of an air bleeding here that goes around the combustor and the compressor and then comes to the turbine itself. So essentially, the role of these air bleeding is to cool down the turbine blades, right? Which is going to mean that your turbine is going to be operational at higher pressures. Okay? Any questions so far? No. So let's move on. This is just a little bit of history, and afterwards, there has been many innovations in the jet engine industry, but the system, like the operating basics of a jet has remained the same, hasn't changed that much. What are the type of innovations that we have seen in the past years? Most of this innovation has been brought on or has been added to the jet engine design in the United States using the U.S. companies, which started with the German, actually, scientists. Most of them started with the German scientists, were brought over after the war, right? Which is the case for most of the aerospace industry. So the first part, the first innovation that we want to talk about is a multi-spool configuration, which essentially means that we are going to have a different stages of compressors. We are going to have a high pressure compressor. Yes.
So it may sound silly, but how did they in 1940s came up with the blade compressor idea? Or how they come up with the design that is going to compress instead of using a different compressor?
They already had the compressors, but I don't know how did they come up with the idea. It's just, I don't know that much of a history about it. Yeah, I don't know that much of a, I don't know the history behind the actual compressors. I'm pretty sure you can find some material on it. Okay, so let's go back to this. We have the multi-spool compressors, which essentially means that we are going to have compression at different stages, right? The first one is the high pressure compressor, intermediate pressure compressor, as well as a low pressure, intermediate pressure, and also the high pressure compressor. So compression happens at different stages, which is going to mean that we are going to be able to compress the air a little more, and it's going to be a little more efficient when compressing the air. And this idea was implemented by Pratt & Whitney, which is one of the leading jet engine design companies. I assume there is at least one person here who wants to work in Pratt & Whitney. Yes or no? Does anyone have, did you know about Pratt & Whitney? Yes? Is there anyone who wants to work there? Yeah, I'm definitely with you on that. But yeah, it's the engine industry is always a war industry, so there's no escaping from it. The next innovation that we want to talk about in the compressor part is the variable stator. Can we think of? Can you tell me what you think of variable stator? What do you think it is? That's the question. Or if you know what it is, can you? What can rotate within the engine? The stator blades can rotate. That's the idea. So essentially, the blades of the compressor are going to rotate, right, inside the engine. Well, what is the benefit of it, though? That's true. That's true. What are we trying to avoid here? Redirecting the flow to where? It's just an actual thing, right? So you want to have it. What is the importance of that? This is essentially with this changing of. Let me actually show this to everyone, just to make sure we are. This is what we're talking about. This is a CAD design of a stator, a variable stator. So we can actually change the angle of the stator, change the angle of attack, right? Angle of attack of this specific blade. So what is the benefit of the changing of angle of attack? Yes.
Depending on the altitude and the speed, we can adjust the amount of air that we're letting in the compressor.
The amount of air we are letting in the compressor. Okay. I don't see how it would change the amount of. I mean, you're closing it and opening it. Is that what you're saying?
For example, on the ships, on the propeller, depending on the angle, that's the amount they're going to push the water out. So when we have either angle, that means we're going to be shedding more air towards the engine.
Yeah. Okay. Yeah. That definitely that's one of the cases. Circulation within the engine. How would that be beneficial?
It has something to do with making a more even flow through the engine so you don't have much turbulence. So if we're not laminar flow, but it's spinning, but it seems like it's not a smoother direction of lines.
How would it make it smoother?
It seems like it might, I'm not sure.
I would say actually it would work the other way because you're essentially creating an obstacle in front of the flow, right? And how would you generate a turbulent flow? By putting a turbulent generator, a vortex generator in front of the flow. This can act as a vortex generator, right? So the flow, I would say that is actually going to enhance the mixing of air, which is, what else? Which can be, I guess, beneficial. Right? So we are changing the pitch of the blades, essentially. That's the idea, right? What happens when you change the pitch of something?
Control the air that gets into the engine so you can like change stuff.
That's the idea that was brought up by Drew and Krim, right? Which is just, yes. There is one more thing that I want you to think of and
It changes the thrust created by the propeller.
the thrust created by the propeller.
Which in this case, I guess, turns out to be like compression.
Okay, so it will affect the compression, that's for sure. That's the reason we have it. You want to increase the compression efficiency, if you want. How would it minimize drag? What will happen? Let me rephrase the question. What will happen to the stall of these blades? Because the air on the blade itself, the jet engine itself can stall as well. It is not just the wing, right? What will happen to the stall of these wings, of these blades? We are changing the angle of attack, yeah? What will happen to the stall of the wing, of the blades? I'm specifically asking about a stall. You can control the stall, right? That's the idea, which essentially means that you can operate this compressor at higher angles, right? But the angle that your compressor sees is going to be lower, right? This is an important thing, right? So that is one of the things that I wanted to make sure we discuss about the variable stators. And the transonic compressor. Transonic compressor is actually used for mostly supersonic flows, or transonic flows in that example. The thing is, we can design the blades based on the innovations in manufacturing and all of those things, the improvements in manufacturing and optimizations in manufacturing. We can design the blades in a way that can produce transonic flow in front of the blade, right? So you're going to have local transonic flow and local subsonic flow around the blade, which means that you can have actually a higher compression ratio using the compressor. So a lot of innovations when it comes to compressor, and actually not just the compressor, but also especially, not just the compressor, especially the combustor chambers. Combustor chambers have come along there, especially their size. Their size actually has changed dramatically, which means that when you have a smaller combustion chamber, you are going to have a smaller engine, you're going to have a more optimized engine, you're going to have a more powerful engine compared to, if you are comparing the sizes. And for a smaller engine, you can have a more powerful engine. We actually have been able to control the emission of the engine using different combustors. I don't really see why is that beneficial, especially because most of these optimized engines are usually installed on fighter jets, and emission is not the biggest priority, biggest problem with the fighter jets, right? Because the goal is, emission is not the first priority. But
would you argue that emissions would be for stealth operations at that point, I guess?
That's a good point. But
But when you say like emissions, you're thinking more like the gas, the exhaust, like actual gas, and like it's chemical.
so that's a good point. But the point is that these radars that they use to like find the fire jets, they don't usually have this. They can't measure the chemical makeup of the exhaust gas, right? So the metallic body of the plane gives it away sooner than the exhaust gas, right? Right? I guess that.
Yeah. But the exhaust is not done the heat
The heat signature part, you can actually that can be a complaint. That can be an interesting idea. But again, the emission doesn't really. I mean, it doesn't really mean you're reducing the exhaust temperatures. Yeah, it's. I mean, my comment was just a comment. Don't like. It is definitely, I guess, lower emission is better for the environment. Right? It doesn't matter if it's on a fighter jet or just a regular airliner.
Changed about a good list, like in the videos it said that material science is the problem with the heat is the material couldn't handle the heat, so what did they call it? They call it like alloys or like a ceramics kind of question? Like what's changed?
No, the type of alloy itself has definitely changed, but the type of fuel they're using has also changed. That's something that Ron works in. And jet fuels, the makeup of the jet fuels itself actually has changed dramatically. So you can, let's not get into the chemistry discussion of it, but
I was just wondering how the combustor chamber has changed.
You know the materials used in designing the combustion chamber has definitely changed, and that has contributed to a better material. But the size of combustion chamber is directly related to the type of fuel that has changed. Like how much of the let's think of it from an internal combustion perspective. How much of a spark you need to combust the gas, right? How much fuel you need to be able to have the combustion with a small spark. Right? Does this make sense? So these are the things that have changed specifically. But if you are someone who is interested in like working on combustion chambers specifically, you can always talk to Dr. Vaughn. He is looking for new students. We have John here, has already joined his group. Dr. Farooq's group, right? But he's in the group meetings. So, and they have a lot of interesting discussions about fuel mixtures. Yeah. I didn't really answer your question, but yes. I hope I cleared it a little bit. Okay. So we have had innovations in the compressor, we have had innovation in the combustor, we have had innovation in the turbine blade material, all of those things. With manufacturing of better turbine blades, more heat-resistant turbine blades, it means that we can have turbines operating in a higher temperature, right? Which we didn't really have before. And also the exhaust nozzles have changed, and the design of the exhaust nozzle have changed dramatically. Actually, this part has contributed to a lot of innovations in the flight mechanics, in the flight of a plane itself. An example of it, a specific example of it that is always interesting to me and to the students is the thrust reversing and also the thrust vectoring. Is there anyone who can comment? Do you know what thrust reversing is? If no, what do you think it is? Do you have any ideas? Yes.
Well, I would think that it's kind of like how, like, if you think of like a space shuttle and stuff, like they have like the vectors that like it can help control the aircraft without having to rely on like the wings and like the other structures that enable mobility. So you can more so like change the direction of it without having to put a lot of force on those components that are like fragile and like stuff like that.
That's true for both of them, thrust reversing and thrust vectoring, right? Do you want to? Redirecting thrust. But how do we redirect thrust? Let's go with the thrust reversing. That's the first one. How do we redirect the thrust? Panels. Just, yeah, so that exactly. So this essentially, yeah. Let's actually watch this one. That's for the thrust reversing.
In this video, I will discuss about the thrust reversal system used in gas turbine engine. As we know, different deaccelerating devices installed on current commercial aircrafts. These aircrafts are generally turbine powered and are normally so heavy and land at such a high speed that the aircraft brakes and spoilers cannot be depended upon for the complete speed control while the aircraft in its landing role. So a thrust reversal system used in
Yes, actually, we don't need to watch all of it.
thrust reversal. Transport category aircraft powered
This is what I
controlled by the
want to
pilot
show you.
by a series of flexible drives, gearboxes, and screw jacks,
So
or
essentially,
by
the idea is you are going to redirect the flow in this direction, right? Instead of having it go out of the exhaust, the direction of the flow is going to change using different mechanisms. One of them actually was mentioned by Drew, right? You mentioned. And the Boeing, let's see what else we want to see here. Yeah. And this is, what's that, by Igor? Yeah, Igor. You sit close to each other, so that, same to me. Yeah, we can actually have this clamshell type thrust reversers that are going to redirect the exhaust flow in the other direction, which means that we're going to have a thrust force in the other direction. That's how we are going to reverse the thrust, right? But the other thing, that the other innovation, that's an interesting innovation, is the thrust vectoring. Thrust vectoring, we essentially change the angle of the exhaust nozzle. Right? Again, what it does is it is going to change the direction of the thrust. So thrust can actually act as a lift force, right? In the direction, I mean, it's not a lift force, but it is going to act in the direction of lift, or a drag, right? Or a weight, right? Or weight of the aircraft. Also, it can act as in the direction of drag with thrust reversing, right? I have another clip that I want to show you. It is yes. It is the thrust vectoring. It is usually done, as far as I know, it is usually done by the direction of the exhaust nozzles. But it is a little easier to handle. Specifically on F-35s, F-35s can actually land and take off vertically, right? They don't have to move on. That's done by the thrust vectoring. So this is the mechanism of thrust vectoring. Very interesting mechanism. As you can see, the wings themselves don't really move that much. So it is not that there's no flaps on it. I mean, there are flaps, but the flaps are not really contributing to this movement. It is mostly the tail wing and the thrust vectoring. I haven't sat in a fighter jet, so I can't really, but I assume so, yeah.
Well, I think it would be more like a computer-based program. Where it's a bunch of reverse and it's still research resource.
Okay, is there any questions?
Say the thrust vector kind of works like when you're backing up a vehicle or something, you have to go down, you have to push up, or like that. So like, you turn one leg and then the other one. Because I give the force with like in the left picture there, if the force is going up, would it get pushed the nose
Oh yes, it really depends. It really depends on the amount of force. Actually, it is very important there. But just for a regular thrust, it is going to act on the center of gravity. So if you are pushing the tail of the aircraft up, the nose is going to go down. Yeah. 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 Okay. So let's move on. And there have been more innovations in the past years in the advances in computational fluid dynamics, as well as the micro electromechanical systems, MEMS devices. They actually have. There is one of these companies. Is it Boeing? I don't remember if it's Boeing or another company, but they are working on a micro jet engine, a very a small size jet engine. And I mean, I guess I assume you would guess that one of the main problems they have is the combustion chamber, right? The airfield, if you are dealing with a micro jet engine, the air molecules are going to become important, right? Because it is a micro jet engine, air molecules are not as small compared to the size of the engine anymore. Also, the fuel-air mixture. All of these things are going to be very important. But how are you going? It's I can actually show. I don't know if I have a picture of the. It's a micro size, so not the size of the hand. Definitely smaller. It doesn't mean it's operational, but they actually have the turbine. I have the picture here. I don't have a picture here. Yeah, these are small. I guess the purpose is to have micro thrust producing devices, right? You know, this is a very specific. I don't really work for the company, and I'm pretty sure based on my country of birth, they won't let me go into the room, and so yeah, that's a very. But I don't know. I assume they're expensive.
I imagine it's like a really small too. You think a lot of RC planes that already create like micro jet engines are like this size. So just for like the idea of just being able to create, it's like the same reason you went to the moon, I guess, just to say that you did it. You know, there's not really any. Yeah.
Are you talking about the micro jet engines or? Okay. Yeah, I guess they don't have combustion there. But interesting discussion though. So hopefully at the end of this lecture, you can design your own micro jet engine. I don't think so, but yeah. There's also different types of new engine concepts altogether, like the advanced turboprops and gear turbofans, advanced air-breathing rocket technology, wave rotor topping cycles, a lot of different advances. But let's get to the mathematics part of today's lecture, right? So, as I said, we usually use the Brayton cycles for jet engine. But there's this idea, there's this different cycle analysis called the Humphreys cycle, right? Which is different from the Brayton cycle. Here, you have the PV diagram and the TS diagram of a Brayton cycle and a Humphreys cycle. Which one is the Brayton cycle? Go back to no. So 1, 2, 3, 4 is one cycle. 1, 2, 5, 6 is another cycle. 1, 2, 5, 6. We have one vote for 1, 2, 5, 6. Yes. You would. 1, 2, 5, 6. That's correct. So this is the original Brayton cycle. which is usually used. But there's this new idea that the combustion happens during a constant volume phase, right? And this is the Humphreys cycle. The Humphreys cycle, this efficiency is calculated a little differently, and it is more suited for some specific new types of engines, specifically about the last type that is not operational, the wave rotor topping cycles, engines in general. We're not going to go into details about this. As long as you understand the difference between Humphreys and Broughton, it should be fine. And the only thing that we actually are going to analyze about the Humphreys cycle is its efficiency. So the efficiency of a Broughton cycle, this is a cold air standard cycle, is calculated by this formula, but the efficiency of a Humphreys cycle is calculated based on this formula. And keep in mind that this gamma is actually K from the previous discussion. So this ratio of a specific heat for air, we usually assume it's 1.4. Any questions so far? Okay. Let's move on. We have the efficiency difference, and the efficiency as a function of combustor's exit temperature. So on these plots, which state is the combustor's exit state? 4. We have 1 vote for 4. Let's actually go one by one. You're still thinking. Which state is the combustor's exit state? Yeah, 1 votes for 3. 3 here, 5 here, right? But it's usually 3, right? We have one vote for 4 and 6. What else? John. 3 and 5. What was your name again? Camden. 3 and 5. 3 and 5. Emery. Is everyone else 3 and 5? Okay. Which is true. It's 3 and 5. The thing is you have the inlet here, the compression stage, then you have the combustor stage or combustor process, and 3 or 5. You have the turbine and then the exit part, which makes your cycle complete, right? So we have a plot the efficiency as a function of the combustor's exit temperature. The efficiency for a Brayton cycle is not going to change based on the combustor's exit temperature. It is not a function of combustor exit temperature. But a Humphreys cycle is a function of combustor's exit temperature. In general, a Humphreys cycle is going to give you better efficiency, but as you increase the combustor's exit temperature, your efficiency is going to drop. But even at 2500 Kelvin combustor exit temperature, it is still higher than the Brayton cycle. So this is actually a cycle that is going to replace the Brayton cycle in the jet engine design, right? So they are going to design engines that is going to work based on free cycle. I mean, that is destined to.
Do you happen to know off the top of your head at which point the Humphreys goes below the Brighton?
No. It doesn't necessarily go to below the brightness. The thing is, it can, okay, you can, let's actually do this. How can we determine when these efficiencies are going to become equal? Set them equal to each other, right? Right? And based on that, you can actually find the value for the combustor's exit temperature based on these two values, right? So do this as a bonus point. At what T3 Humphreys, I'm going to just use H, eta thermal of H is going to be equal to eta thermal of Brighton's. I'm guessing, let me not guess, let me just ask you this. What's that? That's a good guess, man. But, okay, based on these two equations, can you actually give me a straight number? Just can you give me 4,000, for example? Why not?
We don't have any numbers given to us.
Yeah, T1 and T2 are not given, right? As a ratio of the input temperatures. But the thing is it actually, can we just find a number for T1 and T2 online, whatever, from the book, and just put it there? If we do this, a standard number, right, a real number, should we get the same results? The gamma doesn't change. It is air, right? It's 1.4. Should we get the same results for T3? Why not? So this ratio is going to change for different turbines. Is that what you meant to say? I guess. Yeah, so when this ratio is changing, probably your T3 by T2 is going to change, which means that your T3 is going to change. But let's do this, actually. Look up a number for your bonus point. Look up a number, look up a real, turbojet. But look up its T2 and T1, right? And give me a value for T3. This is pretty straightforward. I'm pretty sure you can find many examples of jet engines online, right? Okay. See, one question can lead to a lot of work for you guys. But it's bonus work, so you don't have to do it. I don't want to discourage you from asking questions. It's it's 0.5% of 100% of your grade. So it's essentially as it is worth as 1/8 of a homework. Okay. So again, I guess if you submit 2 bonus points, you can let go of 1 question on the homework. And bonus points are pretty easy. You just have to set these two equal to each other. That's it. Right? That's pretty easy. Isn't it easy? I mean, it is easy, right? You can actually, you don't need to really do it. You can just put in Excel and plug those numbers in. It will give you a value. Or you can actually do it in Google because it will direct you to Wolfram Alpha, which does it for you. So it is pretty easy. You have to be, I guess, a lazy engineer to think of these concepts, right? Like me. We talked about the new engine concepts. One of these new engine concepts that I'm really intrigued with is the pulse detonation engines, or PDEs, right? They're pretty self-explanatory. So we are actually working with detonations, right? With explosions, the small explosions, essentially. And what this idea is going to be used for is for ramjets. So for ramjets, instead of having a turbojet in front of it or wherever active, we can actually use this pulse detonation concept to produce the thrust needed for ramjets in lower speeds, right? So we have like pulse detonations. It's very self-explanatory, right? And pulse jet. What is a pulse jet? You have to speak up. I can't hear.
I can't quite remember, but it has something to do if there's like fuel in it and you ignite it, then it can just kind of get shot out the back and maybe that like.
That's the idea. That's the idea. Exactly. That's essentially the idea. And it will be active until you get to that high speed, and then the ramjet comes into play afterward. I actually have the picture of the turbine blades I was talking about. These are the micro turbine blades. As you can see, they are obviously very small. That's, I don't have the original picture, but as far as I remember, it is 1 micrometer. So this is essentially a 2 micrometer radius. Yes. It is very small. It is very small. These are not operational. These are just the ideas that people are working on. So there is one PhD student somewhere in the world spending their life, wasting their life on this one. Yeah, I guess it will work. And there is a specific type of new engine concept that is, to my mind, it is actually most likely to happen in our lifetime, or is most likely to be operational and in our lifetime. And that's the ground to space engine. I don't remember the exact name. Let me actually look up the exact name in the. No, I'm not talking about the reusable ones. It goes from. I can't believe I forgot the name. Then you are not speaking. Yeah, from takeoff to space, not ground, takeoff to space, right? The combined cycle engines, essentially. Takeoff, not ground. Essentially, the idea is that you start with a turbojet, and this turbojet turns into a ramjet as you increase the speed up to Mach 15, whatever. And this ramjet becomes a rocket at some point, which means that you can actually start from the ground, from takeoff, and go to a space with just one engine. And this is a pretty neat idea. I think this is something that can be actually operational pretty soon. Is there any questions?
So if I make that engine, I'm going to be like a billion.
They are already working on it. I'm pretty sure there are prototypes on it. And there's someone else who is already a billionaire and working on this.
Do they have a variable area nozzle for that?
What's that?
Do they have like a variable area nozzle?
I don't know the details of this type of engine. I don't know. I can't really. But let me put it this way. Most of the new engine concepts have the variable area nozzles because this is something that will come in handy. Right?
When did you ever use the pulse detonation on that engine so that you can just use the ramjet instead of having to?
That's an idea you can work on. You can study this and become a billionaire. That's definitely, yeah. Any questions? So that's all I had for today. And I guess we can stop here unless you have something to ask or you want to talk about anything. and I will see a lot of you later in the evening, 4:30. No, I wanted to cancel today's class, but one of your classmates said the class is going to be canceled, so I thought that we shouldn't cancel the lab one. I don't remember who it was. No, I'm just kidding. We need to talk about the project. For you, there are like 25 more students in the class, so. We have, I guess we have 9 minutes left of this class. I mean, no, but but if you have a question about it, I can answer your question now. That's all right with me, but we definitely need to cover it in the class with the rest of the class.
Theoretically design an airplane for a different class. Can we use that design in this project?
That design is a different design. Are you talking about the aircraft design?
Yeah.
So that is the design on paper. You don't really design an aircraft and fly it. So yeah, you can use that aircraft for this, but that doesn't really help you. Does that make sense? So your project was much easier. I went back to the first year project. Yes.
So we're doing this with the partner, right?
What's that?
Are we doing the final project with the partner?
No partners, no.
No.
Lab 1. This is lab 1. If you don't have the lab 1, don't worry about it. I think you and, what is his name? He doesn't have it. What was your name? Joseph. You and Joseph don't have the lab 2. Also, Karen doesn't have the lab 2. The rest of you have already passed it or are in the class. Yeah. I guess that's it, guys. If you don't have a question,